Hello everyone and welcome back. In the previous video, we looked at how LTE networks save energy. We covered dormant mode, carrier switch off, secondary antenna deactivation, common channel power control, cell DTX, compensation cells, and OAM or signaling based control. In this video, we move from LTE to 5G NR. The important point is that 5G NR is not only faster than LTE, it also introduces a more flexible and energy-aware radio design. With LTE, a lot of energy saving story was about switching off or reducing things that were already active. With 5G NR, the radio interface itself is designed to create more opportunities for sleep, more granular resource activation, better beamforming, more flexible bandwidth usage, and higher efficiency per bit. So in this video, we will look at why 5G NR is more energy efficient by design, while also explaining why 5G sites can still consume more absolute power if they are not managed carefully. Let us start with the shift from LTE energy saving to 5G NR design. In LTE, energy saving relied heavily on operational mechanisms. For example, switch off a carrier when it is not needed, put a cell into dormant mode, reduce common channel power, use cell DTX, switch off a capacity cell and let neighboring cells compensate. These mechanisms are useful, but they are often applied to a system that still has many always-on behaviors. 5G NR changes the starting point. Instead of only managing what is already active, 5G NR introduces a radio design that creates more and longer opportunities for saving energy. It does this through a leaner carrier design, more flexible resource use, bandwidth parts, carrier management, DRX, massive MIMO, beamforming, and more intelligent control. So the move from LTE to 5G NR is not just a move from 4G to 5G capacity, it is also a move from operational energy saving towards energy efficiency being built more deeply into the radio design. The key message is this: LTE introduced practical energy saving mechanisms. 5G NR gives us a more flexible foundation for doing this more intelligently. Now we come to what I call the 5G energy efficiency paradox. On one hand, 5G NR can be much more energy efficient per bit delivered. It supports higher spectral efficiency, wider channels, more advanced antenna techniques, better scheduling, and more flexible use of resources. This means that for each unit of energy, the network can potentially deliver far more useful data than earlier generations. But on the other hand, 5G sites can also consume more absolute power. There are several reasons for this. 5G may use wider bandwidths, massive MIMO radios may have many transceiver chains, there may be more antenna elements, more signal processing, more capacity layers, and more cooling requirements. So we need to distinguish between two things. Energy efficiency per bit can improve significantly, while total site power can still increase if everything remains active all the time. This is why intelligent design and operation matter. 5G NR's advantage is not just that it can deliver more capacity, the advantage is that it can deliver that capacity more efficiently, especially when resources are activated only when they are actually needed. So the goal is to get the best of both worlds, higher efficiency per bit, but without letting absolute power consumption grow unnecessarily. One of the most important differences between LTE and 5G NR is the move towards a leaner carrier design. In LTE, cell-specific reference signals and other regular transmissions are sent very frequently. This creates an always-on behavior. Even when there is little or no user traffic, the transmitter still has to remain active for regular signaling. This limits sleep opportunities. If the radio keeps waking up every millisecond or has to transmit frequent signals, it becomes difficult for hardware components to enter deeper, low power states. 5G NR was designed differently. NR avoids the LTE style always on cell specific reference signal design. Instead, essential signals such as synchronization signal blocks are transmitted less frequently. For example, SSBs may be transmitted periodically, such as every 20 milliseconds, depending on configuration. This creates larger gaps between essential transmissions. Those gaps are very important. They give the radio, baseband, and other components more opportunities to enter microsleep or other lower power states. So the lean carrier design is not just a theoretical improvement, it creates practical time domain opportunities for energy saving. LT had frequent always on signaling. NR reduces unnecessary always on transmissions and allows the base station to sleep more often and potentially more deeply. Why do these sleep opportunities matter so much? The reason is that energy saving in a base station depends on whether hardware can enter lower power states. If the network is fully active, all key components remain powered and ready. That gives maximum performance, but it also consumes maximum power. If there is a short quiet period, the radio may be able to enter a micro sleep state. This gives modest savings because the sleep period is short. If there is a longer quiet period, more components may be muted or switched off. That can create light sleep or deeper sleep opportunities. The deeper the sleep state, the more energy can be saved. But there is also a trade-off. Deeper sleep may take longer to exit. The network must wake up quickly enough when the traffic arrives, when the UE needs service, or when mobility and paging requirements need to be supported. This is the balancing act. We want longer and deeper sleep because that saves more energy. But we must maintain service responsiveness, coverage, mobility, and user experience. This is why 5G NR's linear design is important. It creates longer quiet periods, and longer quiet periods make deeper energy saving states more practical. The challenge is to maximize sleep time while minimizing any impact on the performance. Even with 5G NR, the biggest opportunity for energy saving remains low and medium load operation. Mobile networks are built for peak demand, but most cells do not operate at peak load all the time. A cell may be very busy for a few hours, but for much of the day it may carry low or medium traffic. This is especially true in residential areas during working hours, business districts at night, rural areas, and cells that mainly serve occasional hotspots. At high load, the priority is performance. The network needs capacity, throughput, and reliability, so there is less room to switch things off. At low load, there are many sleep opportunities. If there is little traffic, the network can potentially reduce active bandwidth, deactivate secondary carriers, reduce radio activity, or allow components to sleep. At medium load, the situation is more interesting. The network still has active users, but it may not need all resources. Smart adaptation can reduce energy without affecting the experience. So low and medium load conditions are where energy saving features can have the greatest impact. This is one of the most important ideas in 5G energy efficiency. Focus on the periods where the network is over prepared for the actual traffic demand. Now, let us look at bandwidth parts or BWPs. A 5G NR carrier can be very wide, but a UE does not always need to operate across the full carrier bandwidth. A bandwidth part is a configured portion of the carrier bandwidth with its own numerology and configuration. In simple terms, it allows the network to activate only the part of the carrier that is needed for a particular UE or service. This is very useful for energy efficiency. For example, if a UE only needs a small amount of data, it may not need to monitor or process the full carrier bandwidth. It can operate in a narrower active BWP. Inactive BWPs do not need the same level of processing, which can reduce unnecessary activity and power consumption. BWPs also support flexibility. Different services can use different bandwidth configurations. A low demand service can use a narrower BWP, while a higher throughput service can use a wider one when required. So the energy benefit is simple. Activate only the bandwidth you need when you need it. This is a big step towards more granular resource use in 5G NR. Carrier aggregation is another important part of the 5G NR efficiency story. 5G can combine multiple carriers to deliver higher capacity, better coverage, and higher user throughput. But not all carriers are needed all the time. Typically, one cell or carrier may act as the anchor, while secondary cells provide additional capacity when needed. When traffic is high, secondary cells can be activated to provide more throughput. When traffic is low, those secondary cells can be deactivated, put into a lower activity state, or managed in a way that reduces unnecessary energy use. This is similar in principle to what we saw in LTE carrier switch off, but 5G provides a more flexible and dynamic environment for managing these resources. Secondary cell management is particularly important because additional carriers mean additional radio resources, processing, and power use. So the goal is not to avoid carrier aggregation. Carrier aggregation is extremely useful for performance. The goal is to use it intelligently. Use multiple carriers when capacity is needed. Reduce or deactivate secondary cells when they are not needed. That gives us the best balance between performance and energy saving. Next, let us look at UE DRX and network readiness. DRX stands for discontinuous reception. It allows the user equipment to switch off its receiver for periods of time and wake up only when it needs to monitor for control information or receive data. This is mainly a UE power saving feature. It helps improve device battery life, but it also matters in the wider energy efficiency story because the UE and the network need to coordinate properly. If DRX is configured well, the UE can sleep longer without missing important network activity. But the network must remain ready. It needs accurate scheduling and paging. It needs good timing alignment. It needs to understand traffic patterns and service requirements. It also needs to avoid making the UE wake up too often unnecessarily. This is especially important for applications with different traffic characteristics. A smartphone browsing session, an IoT sensor, a video stream, a voice call, and an industrial device may all need different DRX behavior. So DRX is a good example of how energy saving is not only a network side issue, it is also about coordination between the UE and the network. Longer UE sleep cycles can improve battery life, reduce unnecessary monitoring, and support better overall energy efficiency as long as the network remains ready to deliver services when needed. Massive MIMO is one of the most important technologies in 5G NR. It improves spectral efficiency by using large antenna arrays and beamforming to serve users more effectively. It can increase throughput, improve coverage, support more users, and deliver better performance per unit of spectrum. From an energy efficiency point of view, massive MIMO can be very powerful because it can deliver more bits for the energy used. This means better energy efficiency per bit. But massive MIMO also adds complexity. A massive MIMO radio has many antenna elements, RF chains, and signaling processing requirements. If all of these remain active at all times, the site can consume a lot of power, especially when traffic is low. So massive MIMO has two sides. It can improve efficiency by delivering far more capacity and better beam control, but it can also increase absolute power consumption if not designed and operated carefully. This is why energy saving features such as antenna adaptation, RF chain management, beam management, and low load optimization become so important. Massive MIMO delivers big gains, but only when it is designed and operated intelligently. Beamforming is closely linked to massive MIMO, and it gives us a useful way to think about energy focus. In a traditional omnidirectional transmission, energy is spread widely. Some of that energy reaches users, but some is wasted in directions where there are no users. With beamforming, the antenna system focuses energy towards the user or the area where the user is located. This improves signal quality and can reduce interference. It can also allow the network to achieve the required performance with lower transmit power than would otherwise be needed. In energy efficiency terms, beamforming helps the network avoid wasting energy. Instead of broadcasting everywhere at high power, the network can focus energy where it is useful. Of course, beamforming requires channel measurements, beam calculation, beam management, and continuous adaptation as users move or radio conditions change. So again, there is complexity, but the principle is very strong. Use energy where it creates value. Beamforming focuses energy on the user, improving performance while reducing wasted power. It is also important to remember that 5G energy efficiency is not only about standards. Hardware matters. A network feature can create a sleep opportunity, but the actual energy saving depends on whether the hardware can take advantage of that opportunity. Important hardware elements include RF chipsets, power amplifiers, active antenna units, radio units, cooling systems, power supplies, and the ability to switch off subcomponents. For example, a more efficient power amplifier can reduce power consumption per transmitted bit. Smarter cooling can reduce energy used for temperature management. Better integration can reduce losses between components. More advanced radio units may be able to deactivate unused modules, carriers, RF chains, fans, or processing blocks when they are not needed. This matters, especially at low load. If a radio unit cannot shut down subcomponents, the network may create a theoretical sleep opportunity but achieve only limited real energy saving. So standards create the framework, but hardware makes the savings real. The best results come when 5G NR radio design, intelligent control, and efficient hardware all work together. So what does 5G NR set up for 5G Advanced? 5G NR provides the foundation. It gives us lean carrier design, more sleep opportunities, bandwidth parts, carrier aggregation and secondary cell management, UE DRX, massive MIMO, beamforming, and improved hardware capabilities. These are all important building blocks, but in early 5G, many of these features were not necessarily packaged as a single explicit network energy saving framework. That is where 5G Advanced comes in. Release 18 builds on the 5G NR foundation and introduces more explicit network energy saving capabilities. The idea is to make energy saving more standardized, more coordinated, and more granular. Instead of simply relying on general 5G flexibility, 5G Advanced begins to define more direct mechanisms for reducing RAN energy consumption while maintaining performance and user experience. So 5G NR gives us the foundation. 5G Advanced builds on it with a more targeted energy saving toolbox. That brings us to the end of video 3. In this episode, we looked at why 5G NR is more energy efficient by design. We covered the shift from LTE operational energy saving to 5G NR radio design. We looked at the 5G energy efficiency paradox, where 5G can deliver better efficiency per bit while still requiring careful management and absolute site power. We then looked at lean carrier design, sleep opportunities, low and medium load operation, bandwidth parts, carrier aggregation, secondary cell management, UE DRX, massive MIMO, beamforming, and hardware evolution. The main message is that 5G NR provides the building blocks for more energy efficient mobile networks. But the story does not stop here. In the next video, we will move into 5G Advanced Release 18 and look specifically at network energy saving features. We will cover SSB-less S-cell operation, cell DTX and DRX enhancements, antenna adaptation, PDSCH power adaptation, restricted paging, conditional handover enhancements, and XN signaling for energy saving coordination. This is where energy saving becomes more explicit and more standardized in 5G Advanced. Thank you for watching. If you found this video useful, please like the video, subscribe to the channel, and check the links in the description for additional resources. We hope to see you again in video 4. Goodbye.